All right. So I wanted to start off where I finished last time, which was with the following definition. So a rigid TT category F, not zero, is TT field if, so I think maybe this was a condition last time and now it's not, but that's okay, it doesn't really matter. So somehow the important one, or the first important one, is that for every x in F, not zero, tensoring with x is faithful. And then the other condition, which I think I should spend some time on because it confused some people last time, which is fair because it probably also will confuse me, is that if I look at this category of functors from f of to mod z, and I put this decoration z here, this is locally Noetherian. And so let me explain what on earth I mean by this. So first of all, what is this category? So F is triangulated. So in particular, it's an additive category. It's enriched in abelian groups. And so I can forget everything about it except that it's enriched in abelian groups. And I can look at the ab-enriched functors from F op to abelian groups. So that's what this little z means. So I want my functors to be homomorphisms of abelian groups on the Hom sets. So if you like, I want finite sums to go to finite sums. And that's like all of the structure I'm considering on this. So I'm not doing something fancy, like I'm not taking like spectral presheaves or anything mad like that. Like I really just want additive functors from f op to mod z. And so the reason I write it like this is if you look at functors like this out of some additive category, that's the analog of taking modules over a ring if the ring had several objects, right? So if my additive category had a single object, up to sums and summons, this would really just be modules over its homomorphism ring. So this is some category of modules. And so this is a nice abelian category, so I can compute kernels, co-kernels, sums, whatever I like, point-wise in the target. And so, do I want to say anything else before I say what locally Noetherian means? Oh, maybe not. Probably I do, but I'll just forget. That's okay.
Can I ask a quick question?
Yeah.
So locally finite is not good enough?
So I think it's gonna, if it's locally Noetherian,
in examples it will...
So in the examples it'll be locally finite, it'll actually be more than this. And I'm trying to remember, I mean, it being locally Noetherian is somehow not so far away from it being locally finite because, yeah, I'd have to think harder than I probably should now to make sure that that's okay, but there's something there. There's even a remark on this in our paper, I just don't remember what it says. Right, and that's the other thing I was going to say. So maybe some of you might prefer to think of this in a different way. So another way you could think about this is I can think of F again as a small, like Z-enriched category, and I could take its free co-completion. So like respecting the finite sums I already have, I could freely adjoin co-limits to it, and then I would get this thing. So this is like generated under co-limits by the representative functors, which are the projectives. And so locally Noetherian just means, so I guess this is going to end up looking recursive, so that's okay. So locally Noetherian means that mod F has a set of Noetherian generators where some module M is Noetherian if it has the ascending chain condition for subobjects. So like what this boils down to is basically I'm asking that the representable functors are Noetherian objects. So they have the ascending chain condition for some objects. Right. And so I could talk a lot about this category, but I probably won't say much more, but maybe let me make a remark. So if you don't like this, there's a different way of thinking about that. So this is equivalent. So this. This category being Frobenius. By which I mean the injective and the projective objects coincide. So if you don't want to think about chain conditions and being locally Noetherian, you could just ask that in here the representable functors are injective. But I wrote it this way because, you know, this is more obviously some sort of size condition, whereas it's a priori not so clear that being Frobenius is a size condition, but in this case it turns out that it is some finiteness condition. Alright. I mean, so particularly today, right, the last day, people should yell at me, but let me encourage that by asking, does anyone want me to say anything more about this before I move on? Very good.
Could we have some examples?
There will be examples. Like basically, what am I gonna do? I don't know. This doesn't help. I don't know why I look at it. I'm gonna state a theorem, and then basically, I'm gonna talk about examples for like probably 10, 15, 20 minutes.
Are you going to give us a non-example in the sense that the first holds but the second doesn't?
Yes.
Good.
Oh, actually no. So I should say you confused me. So what I was going to say this later, but I should say it now. So this condition, it's not clear that it's not redundant.
Exactly.
So in all of the examples, it's satisfied and it feels like something one would want. So we feel like it's reasonable to impose this, but have I thought about this since then? I still don't think I know an example where the first one holds but the second doesn't, but we couldn't prove that it's for free. Yeah, so this is why I said that somehow this definition is really like a candidate definition. So maybe it can be improved, maybe it needs to be adjusted slightly when we understand more examples better. But we'll see that this is sort of exactly what you get if you take the intersection of all of the examples we understand.
Can you explain why you need arbitrary modules? So instead of saying, so if you take finitely presented ones, then you'll get the Frobenius condition that you see.
So there's a subtlety there. So if I took finitely presented modules, this is always Frobenius. Yeah. And so then I wouldn't have this equivalent condition, but I could ask for the finitely presented guys to just be Noetherian. Although one has to be careful, right, because it's really about finitely generated sub-objects being finitely presented, and if I only look at the finitely presented guys, I don't see those, so no, you need to...
No, it's equivalent. It's equivalent to being that the finitely presented ones are Noetherian objects.
Alright.
In
the category of finitely presented modules, like it's okay to only look at those things? Alright.
Look at Gabriel's case, it's already there.
Good. I mean, I would have been surprised if that wasn't okay, but I tried not to say wrong things. If I have some idea that they might be wrong, which normally I don't. But yeah, so if you drop the locally, you could work with the finitely presented guys. Right, and so I wanted to make a minor correction the last time and justify this definition in some conceptual way. So this is enough to prove that if f to L is non-zero, and so John was trying valiantly to stop me from making this mistake last time, but I was refusing to yield. So thank you, John. Yeah, so my target should be non-zero, and that's all I need, right? Because I always want this function to be monoidal. So as long as this has a unit, the function can't be zero. But if the unit is zero, then I'm in trouble, and that's what you try and tell me. Yeah, so I want L to be non-zero. I want this to be a TT functor, so it's exact, and monoidal with f a field, and maybe I should give this a name, f, then f is faithful. And so this is some sort of fieldy behavior, right? So if I sort of look at TT functors out of the field, I can't lose any information about maps or anything else. And the definition also implies that the spectrum of f is a point. And so this was in the exercise class, I think, although I've already forgotten, but Scott is nodding very gently, so I guess it's true. Yeah, so from like the abstract point of view, this is reasonable. So now let's look at some examples. So kind of the
Could you just say a quick word for the specialist about this term why you don't need big ambient categories?
Oh, yeah. I mean, so
without going into too much detail.
Yeah, I mean, so in the paper, we work with large categories, so rigidly compactly generated things, so we assume all coproducts. But the point is here, so the proof of this is the projection formula. And because we have this condition on
the module categories.
Yeah, so you can do the projection formula for like cohomological and things on the module category. And because even without a model, right, because F is pure semi-simple, you can see the triangulated category inside of the module category. You can check the analogous statement for the big category using the projection formula for modules. Right. Yeah, so the kind of first example one sees, depending on where one comes from, would be we could take a commutative ring, R, we could take some key in spec R. I guess I'm defining a residue field, I don't even need to do that. I could just take a field. So I could take a field K, and then I could pass to the bounded derived category of finite dimensional vector spaces over K. And this category is very easy to deal with, right? Because K is a field, it's global dimension 0, there are no extensions, every triangle is split. This triangulated category is actually abelian, and it's equivalent to the category of Z-graded vector spaces, right? So I just have a grading, which is given by cohomological degree, and under this equivalence, suspension over here corresponds to translation. And I can also write this, which is clear from this point of view because I have bases. I can write it as the additive closure of the suspensions of K. So basically every object is a sum of shifts of the tensor unit in this category. So this is very, very easy. And it also satisfies, yeah, so it's clear from this, right, that it satisfies the first condition. Because tensoring with K is the identity functor. And so tensoring with a sum of suspensions of K is just taking a sum and then with appropriate suspensions, and so that's certainly faithful. And from this, one can check that if I look at the category of modules over dB mod K, this is just equivalent to graded K vector spaces of arbitrary dimension. So I take all graded K vector spaces, and this is certainly a Frobenius category, and it's also not so hard to check that it's locally Noetherian, right? I mean, because K is Noetherian as a graded vector space over itself. And so then we also saw an example that's very similar, so the chromatic version of this. So I can also take Kn, where I fix some prime P, Morava K theory. And then my field would be, and then I have no idea what I'm supposed to write, so let me write this. I could take like kn module spectra and take the homotopy category and take the compact objects, or I could just write this down explicitly as a triangulated category, because the point is that from what Anya's told us about like spectral fields and Morava-K theory, the same thing is true, right? Like every module over this is just a sum of shifts of the Morava-K theory spectrum. And so again, everything's a sum of shifts of the unit. And so this is the point at which it would be reasonable to say, well, like, why would you not just take that as a definition, right? I mean, you have these two examples of things we care about. Like, why do this complicated nonsense when you could just ask that everything is a sum of shifts of the unit in your category, and that would give you a perfectly reasonable definition of field that would make you feel very happy, because it would look a lot like vector spaces, right? Everything would be free after suspension.
So you probably need to worry about Kn might not be useful. So
yeah, I was gonna
just pretend.
I'll close my ears and you can say that to the audience. No, I mean, so of course, yeah, there are some difficulties here depending on whether P is 2 or not, right? But the point is that I can always define everything I want in a stupid way on the homotopy category, and so because I'm only talking about triangulated categories, I'm not going to get into any trouble. Yeah. I didn't mean to rub off the advertisement, but if anyone needs reminding about it, just ask me and I'm happy to give you the details. So we could look at another example. So I could look now at, what do I want to take? Does it really matter? No, not really. So I could look at something like Laurent polynomials with T in degree n. And so this is not an honest field anymore, but it is a graded field. And so I'm thinking of this as just a Z-graded ring. But of course I could grade by other things, and I would get other examples that look very much like this. So then I can define for an integer I and some m a graded F module I define a new module m twisted by I just by saying that its piece in degree j is m I plus j. And if I do that, then the category of finite dimensional graded F modules is just the additive closure of the F i's such that I is between 0 and n minus 1, right? So the point is you can draw a picture of this. I have some gap in F, right? Like there's a jump between the unit and wherever T lives in degree n. And so I have some space to move F up and down and get something that's different as a graded module. So basically I've gone from having something that's a field where the pickup group is trivial to something that's a graded field where I now have like a non-trivial pickup group that looks like Z1 and Z. So I have some invertible objects that are not the unit. And otherwise this story looks exactly the same. So I can take this thing and form the bounded derived category of F graded vector spaces, of graded F vector spaces, and this will be now the additive closure of shifts of these graded free modules, where J can be anything, and I is in my range between 0 and n minus 1.
So keeping the two gradings separate?
Yes, yeah. Yeah, so there are two things I could do here. I could consider DG modules or module spectra, and then I would get something that looked like that. Because I'd be like smushing this internal grading and the cohomological grading together, so I want to keep them separate. So I'm really considering bounded complexes of graded F modules. And so that's why I now have these two gradings. And so every object is a sum of shifts of invertible objects, but not a sum of shifts of the units anymore. So it's still clear that this is a field in the sense I defined, but it's also clear that we need to allow for there to be a pickup group. And so now you could say, well, why don't you make that the definition? And because it still wouldn't catch all of the examples I want to catch. And so now I want to do a series of examples, and I didn't come up with a witty name for them. So I want to look at now the stuff that has been coming up in Dave's series of talks. So I want to look at some stable categories of just cyclic groups. And so K is going to be a field of characteristic P. So I'm going to change P, and K is not going to change, but its characteristic will. And so let's look at some of these in small examples. All right, and so I want to use, and Dave has mentioned this fact, so I'm going to think of KCP as being this truncated polynomial ring Kx modulo x to the p, just because then it's easier for a commutative algebraist like me to write down the modules and stuff. Right. So I can look at the case p equals 2, and then we're going to see something like the examples we've already seen. So actually, maybe let me stick to general p for the moment. So KCP has what's called finite representation type. So that means there are only finitely many indecomposable modules, period. So not like finitely many finite dimensional indecomposable modules, but really just finitely many indecomposable modules. So every KCP module is a direct sum of finite dimensional ones that are indecomposable, and I'm not going to explain how, but, oh actually no, I will explain. I'm not going to explain why that's true. I think it was an exercise from Dave's course, but it's going to be what's going to give us this locally Noetherian condition. And I'll explain why, right? And so the indecomposables look like K, Kx modulo x squared, so they just look like these cyclic modules that you get by killing higher towers of x. So these are the only indecomposable modules. And this guy is projective injective, and none of the others are projective and hence injective. And so when we stabilize, we just kill the projective. So all of the other guys are going to survive to the stable category, and we need to worry about what the maps between them look like, but that's easy to deal with in examples. So let's look at what some of these categories look like for small values of p. So I want to do p equals 2 and 3, and we're not going to see anything that's not already covered by the two examples we did. But then, spoilers, when p is 5, we're going to see why we shouldn't have just tried to ask that everything's a sum of shifts of things in the Picard group. I was doing so well, I had not scraped the squeegee on the board, like, all week. I just did it. I'm like immensely disappointed in myself.
Thank you.
So yes, you can sit down, I will finish your talk, please. Right, so when p equals 2, we only have the first two of these guys, and kx modulo x squared is already projective injective. And so mod kc2 is just the additive closure of the trivial module. So it's the only game in town, and this is equivalent to just a category of mod k vector spaces. So the suspension is just the identity, and really, you know, I should be sent to the gulag for re-education for thinking of this like this. I mean, really, I should think of it as graded modules over this with degree t. So really, this is an example of the second kind. It just looks a bit like an example of the first kind. Right. So this is fine. Again, everything is just a sum of actual copies of the unit, no suspensions involved, and so it would cover our definition, right? Oh, and now I should say, I mean, in this case it's clear, but why will these always satisfy this locally Noetherian module category condition? It's because if I look at functors out of this category that are additive, they're determined on what they do on the finitely many indecomposable objects. So I'm basically looking at modules over the endomorphism ring of the sum of those guys in the stable category, and that's a finite dimensional algebra. So this category of modules over my finite dimensional algebra is certainly locally Noetherian. It's even locally finite. Alright. So I could go up to p equals 3. I mean, I don't know why I'm insisting on doing this one, but anyway, whatever. And so now there are 3 of these modules, and we lose one of them. So it's the additive closure of k and k x modulo x squared. And one of these is the suspension of the other. So again, everything is a sum of shifts of the unit object. And so it's evident that this is a field because tensoring with k is faithful and tensoring with the suspension of k is faithful. And so not much is going on. Although here I do lose this very easy description because sort of the gadget controlling this is not formable anymore, so it's somehow more complicated, but it's still of this example type. Right. But then I could go to the prime 5. And so now I'm going to have 4 guys that stick around in the stable category of the cyclic group of order 5. So everything is going to be a sum of shifts of k, what I get when I kill the square, what I get when I kill the cube, and what I get when I kill x to the 4th. And the way the suspension acts is it switches the 2 in the middle, and it switches the 2 on the outside. So we can see that not everything is a shift of the unit anymore, right? The only shifts of k are k and kx modulo x to the 4th. So the best we could hope for is to be in the second class of example. So we can ask, are these guys in the pickup group? Are these invertible? And the answer is no. So I don't know what I'm going to call it, a nothing. So kx modulo x squared is not invertible. So this is not covered by either of the sort of examples we saw so far. And I mean, if you want to check this, you could, for example, compute its stable endomorphism ring, and you'll see like immediately that it couldn't be invertible. Yeah, so this is not invertible, so this is not a case where all objects are sums of shifted universals. But maybe I can still fit the punchline on the board. But it is a field in the sense of our definition. And I would argue that, I mean, that's a bit of a silly thing to say, right? Because our definition was motivated by looking at these examples and trying to catch it. But somehow, like, if you stare long and hard at these examples and think about how they behave, and you think about, like, pi points, like Dave talked about, and cyclic shifted subgroups, in some sense, this does deserve to be a field, and it satisfies this tensor faithfulness property, right? By virtue of being a field in our sense, or by checking directly. And so what would we need to check to see that it's a field? Well, so this second condition about the module category, I explained. So we need to check that tensoring with every object is faithful. And so I'm not going to write down a proof, but one way of doing that is to use that because our prime is 5, and like it's just 5, it's not 5 squared, our modules have dimension 1, 2, 3, 4, and 4, and these are all invertible modulo 5, and that is enough to let you conclude, if you do the right thing, that tensoring with them all is faithful. And so this is an example of a field where somehow the triangulated category on the structure is not trivial in some sense. There are non-split extensions, there's actually interesting stuff happening. And in fact, all of these guys are fields. And so as P gets bigger, these things get more and more complicated, and so you can sort of have these fields that have many objects that are not invertible, many non-split triangles, some actual interesting triangulated structure.
Can you say maybe a little bit more why you want them to be fields? You just said something that...
Oh, I'm gonna...
You will say...
Yeah.
Okay.
Yeah, so this like tensor product being faithful condition is like a restriction already for cyclic groups. So if I looked, for instance, at like mod kcp to the n, so I took a cyclic group of order p to the n, for n at least 2, this is not a field. So for instance, I could look at the permutation module for like cosets of CP inside of there, and tensoring with that is not faithful, like basically because it's got dimension divisible by P and it's indivisible. So this is not a field, but we could look at the inclusion of CP into CP to the n. So this is just a cyclic subgroup, it's not even shifted. And it gives me a restriction functor, which is monoidal from, do I want to write the arrow backwards or the things backwards? I don't know. So I get a restriction functor like this from mod kcp to the n to my field, mod kcp. And so the spectrum of this is already a point, but what this is telling us is that we should think of this as some sort of TT analog of an Artin local ring, and this is its residue field. And this restriction is kind of throwing away some sort of nilpotent tangent information and giving us something that's just a point. So this is the residue field, if you like, at the unique point. of the spectrum of this stable model category.
It doesn't worry you that mod CP has some non-trivial ideals as a category.
No. Like you mean ideals of morphisms?
Yeah.
Yeah. And so that's the thing, right? We somehow, to get this to work, we want to take into account the tensor product, and so it has non-trivial ideals of maps, but not that are sort of compatible with the tensor product. I think
It does.
Am I?
Radically.
You feel that it's more, am I wrong?
He's right.
All right.
Yeah, the same simplification, but this is not the same thing.
No. Yeah, no. No, so I agree. You're right.
You might be thinking about the module.
Yeah. Sorry, I've taken modules one too many times. Yeah, I mean, so.
But that would
That
not
is-
be a triangular factor,
yeah.
as this residue must be exact. Isn't it? For instance, the triangle 1, sigma 1 in PC3 would go to a sequence which has only 0 maps.
Oh, it's not exact, that's
Yeah.
right, yes.
You can make exact triangles with all
Yeah.
maps and the radicals. So
Yeah.
filling the radicals,
Yeah.
would be that.
Yeah.
The equation is actually in a Billian category, not
Yeah.
a triangulated. Yes, okay.
Yeah, but yeah, and so it's certainly true that this category is not semi-simple, right? Like even as a monoidal category, so there are like non-faithful functors out of it, but not that preserve the tensor product of the triangles at the same time. Right. And so now, I guess for the last part, I wanted to talk a little bit about the story in general. So basically present something that we don't know and then maybe, I don't know, ramble a bit because...
Sorry to interrupt, but I think there was a question about justification and you said you were going to say something.
Oh, and then it was you, what did you ask us?
Oh, what? I couldn't hear the...
I was repeating a question from the audience, but I don't know if it was yours, about justification why these would be fields in this.
Yeah. I guess this already helps.
This already.
Yeah, that's what so I kind of hoped that this would be sufficient justification because I'm not sure...
No, I didn't know if you wanted to repeat the pipe on.
Oh, yeah.
Pipe on point that you.
So there would be no other candidate for a residue field, for example, in this case.
Yeah, not if you want this to be both monoidal and exact. So you can do... Yeah, I mean, somehow there are other things you can do. So something else you could do, right? Like if you didn't want to insist that this was exact, you could somehow look at the ideal of maps in here that factored through modules of dimension divisible by indecomposable modules of dimension divisible by P. So basically induced modules. And that would give you an ideal compatible with the tensor product, and you could kill it. And then you get a bunch of copies of this thing, and you could view that as being a triangulated category, but the function wouldn't be exact. And so that's maybe another argument that this should be the residue field, because if you somehow try and kill the stuff coming from induced modules in some reasonable way to get something that's still triangulated, you're going to get a bunch of copies of this as a triangulated category. So it somehow, doesn't matter what you try and do, it will show up.
Thank you.
Right. So I wanted to say something about residue fields, which in principle will not take very long because I can't say very much. So we have our space, spec K, so now I'm going back to K as my, let's just say rigid TT category. And we sort of saw that we have some quasi-compact opens, and they correspond to things of the form K modulo the stuff supported on V, so maybe let me write it like this. So I could ask for this to be closed. And I guess if I'm being careful with quasi-compact complement. And then we have, for P in the spectrum, we have the analog of a stalk at P. So this would look like K modulo the prime. And so it's tempting to ask, can we reduce this further and come up with a residue field, right? So if we were thinking in the commutative algebra context, this would be like passing from R to the localization of R at P. So I invert all of the elements that are not in P. But this still has some non-trivial spectrum, right? It's a local ring, and so it's sort of a bit easier in some ways than R. But really what we'd like to do is pass to some analog of a residue field at P. So something like the passage from RP to KP, right? So by which I mean RP modulo P times RP. And so the challenge is to construct these things, right? And so you know some examples, because if you're in the commutative algebra setting, you can actually just take the base change functor to the perfect complexes over your honest residue field. And similarly, in the chromatic picture, you have the Morava-K theories that serve this role. And then life is harder in ways that I'm not going to talk about in the case of finite groups, and especially finite group schemes. But you have examples like this. So you have these things like secret shifted subgroups and pi points that will give you, to some approximation, something that's like a residue field.
And the functors don't present tensors.
Yeah, exactly. Yeah. So the challenge for you guys, this is the homework. So given P and spec K, produce some pi from K to F, with F a TT field such that the kernel of pi is P. And so certainly this should be exact. And then sort of, as Dave said, I mean, in an ideal world, this would be symmetric monoidal, but maybe one only insists somehow that that the kernel is prime. So sort of it might not preserve tensor products on the nose, but it tells you that if the tensor product of two things was zero, somehow it was already zero when you tensored with one of them because it's in this prime ideal. Because you can check, right, that if I started with a field and I had a TT functor like this, then the kernel would be prime, right? So maybe let me write that down. So like if F is a field, and this is monoidal plus exact, then if pi x tensor y is 0, like that. So this is isomorphic. Pi of x tensor pi of y. And suppose this is not 0. Well then, because f is a field, tensoring with it is faithful, and so pi of y will be 0. So the kernel is prime in that case, right? Because if x tensor y is in the kernel, then without loss of generality, at least one of them, at least y is. If pi x is not 0, you know what I'm trying to say. I'm like completely failing to say it, but that's why you guys are smart. You can interpret what I'm trying to say.
So in this challenge, do you want to impose a sort of surjectivity on pi?
No. And so, I mean, I'm not necessarily asking that this is like the closest field to K. Like, we'd be happy with any field. But then, yeah, this I would have to think about it maybe. I mean, for the actual thing that should be the residue field, maybe it should be essentially subjective, maybe it shouldn't be. I mean, that's just, it would be somehow reasonable, appealing to assume that, but I don't know if
Yeah, whatever you mean by the image, it would still be a subfield of filters.
Yeah.
Field as well.
yeah.
You could probably arrange something. But you have the big.
Yeah, that's true, but then, I mean, these examples where there are non-trivial triangles over here, it makes me a little bit nervous about the image maybe being horizontal extensions. Yeah. Alright. Yeah, and so I can't really tell you anything about how to do this, right? So this is not one of these things where it's like, oh yeah, like I have this problem and I have some ideas, but I'm like too lazy to think about it. Like, I have no idea. I have no idea to the extent that even if you gave me the perfect complexes on a commutative Noetherian ring, and you didn't tell me it was that, I could not construct for you perfect complexes over K. So even in the examples where we know how to do this, and to the extent that's reasonable, we can compute whatever we want, I couldn't tell you how to do it in a conceptual way. Like, all I can do is somehow pull the rabbit out of the hat and go, look, it's the right thing. Yeah, so I'm not gonna, So I don't speak for my co-authors when I proclaim my overwhelming ignorance, but really, no idea, not even a little bit. Right. And so now I have a little bit of time left, and so unless there are any requests, I was going to try and tell you a little bit about what we can do. All right. So we can't produce these things, but maybe let me advertise to you something that we can produce, which is already interesting, even if it's not what we would like. So we could sort of draw the following picture. So really what we'd like is to start with K and some prime and produce a functor to a field. And we don't know how to do this, but we do know how to go. But if we could do this, right, we could go to this category of modules over K, and we could go to the category of modules over F. And so I'm writing little m because, let me just not make that confusion, because it's not going to matter. And so if I had a functor like this, then I would have some functor like this, which would be now an exact functor of abelian categories, which was also monoidal. So one could prove that. And if I had such a functor, I could factor it by some quotient. Right? And so all of these dotted arrows, we don't know how to build. But I could say, sort of, if I had the dotted arrows, could I build this part? And the answer is that yes, we can. And so sort of if we try and implement this, we can sort of build this bit for an imaginary. I guess I should be careful saying that in case people start thinking about number theory.
Shouldn't the functor between the module categories go the other way? I mean, this is supposed to be a restriction along the top, right?
Sorry, I didn't say so. No, I want this to be like a left-Kant extension. Oh, so it should be determined by sending representables to representables and preserving colimits. Okay. So I want the functor in that direction.
Thanks.
You said it's monoidal, so is the monoidal structure data evolution or?
Yeah. So the monoidal structure I put on here is is day convolution, so this will be a monoidal embedding, and then one can check basically by checking on representables that this will also be monoidal. Right.
It's the left adjoint to the one they said.
Yes, yeah, so it's going to be the left adjoint restriction. Right. Yeah, and so the point is that even if we don't know any of this other stuff, like we don't even have an f in mind, we can still build this bit.
What is B?
So I haven't said it. Thank you. So if I give my diagram has now become a complete mess. So if I give my imaginary functor a name, what?
Was called pi or?
Well, no, that's the thing. So this was called pi, but then if I call this pi, I have to pick upper and lower star, and no matter what I pick, someone's going to complain. So I just want to give this a name. So this is supposed to be the kernel of pi. Or the kernel of the empty set, if you want, we can call our functor the empty set. And so we can call this bit a homological residue field. And so the idea is like homological because this mod k is where the homological functors live. It's somehow recording stuff about homological information. Field, because if we've really implemented this, it should be fieldy in some way. And then the residue part's a bit more interesting, but we'll see in the examples that, well, I can say because we're doing this factorization process, it wouldn't matter which f we picked, as long as it sort of belonged to that prime and we crossed our fingers and hoped, we should get the same quotient. And so it should somehow be like a minimal guy in some sense.
How far could you get if you could just make a quotient at the level of the module category that is reasoning, just to produce a homological residue field, but without the actual depth?
I'm not sure I understand. I mean, so I'm going to write this down, but we can always produce the homological residue fields.
Oh, okay.
Yeah. Is that's what you're asking?
That was my question.
Did you guys rehearse the questions?
No, we've known each other for a long time.
Very well timed.
That reminds me, you should give me the list of questions for next week. Right. And so rather than trying to define these things, let me kind of give you some sort of abbreviated sales pitch instead. So we have existence. So for any p in spec A, there exists a homological residue field to, what do we call this? And I guess let me give this a name. What am I supposed to call it? Something like that? Is that what you use? Is that what we use?
Is that H sub P?
Yes.
H bar sub
H bar sub P. And so it's supposed to be like, and maybe H would be this restricted Untitled functor, H bar would correspond to passing with the residue field, and then I'm indexing by the prime I took. Yeah, so you can see while the questions were rehearsed, the talk was definitely not. Right. And so these things, anyway. So these things do their job in some sense, right? So you can say, well, so what? Like you've said some words, you didn't tell me what they mean, and then you've said that you can find these things, and you didn't explain like how you do it or what they do. But they're somehow sufficient for proving things that are interesting. So if I have some map, in K, so maybe I've been very bad about writing any names up, but maybe here I will. So this is some ruminations by Paul Henning and I. And then this one is Paul. I mean, if you hadn't been downstairs, I wouldn't have written any names, but since you're sitting right there, I should. Yeah, so if we have a map, f from x to y and k, and so it's the same as it was before, so k is a rigid TT category, such that h bar of f is 0 for every homological residue field that K has. Then there exists some n such that f tensor n is 0. So, as in like the work of Thomason and Amnon in algebraic geometry and the nilpotence theorem, like the fixed subcategory theorem by Evans, Hopkins, and Smith, these things are sufficient, like the usual fields are, to detect the nilpotence of maps. So this should tell you that somehow we've at least gotten towards making some sort of definition that's correct. So the fact that we can prove that they exist is enough. With some more work to show that they detect nilpotence. And then maybe let me also, extremely quickly write down a couple of examples, right? Because you can sort of, I haven't really told you anything, so it's hard for you to, but you could look at the definition, which is going to involve making some choices and taking some quotient and then writing down some awful abelian category that you, in principle, don't really understand. But it turns out that even if you only cared about fields, the things you produce in examples are actually quite interesting objects. So, for instance, let me write down maybe 2 or 3 examples, we'll see. And so these examples come from work of Paul and James Cameron, and then James and myself. And so this is not acclaimed director James Cameron. This is significantly younger postdoc James Cameron. So if I took R to be a commutative Noetherian ring, and P prime ideal in the spectrum of the ring, which is homeomorphic to the spectrum of the perfect complexes, then the homological residue field at P is the following guy. So I could take the residue field, I can take Tor of the residue field with itself, which is a Hopf algebra, and then I can take the category of graded comodules over that graded Hopf algebra with the induced tensor product. And this is this AP I would construct as a quotient of the category of modules over the perfect complexes. So somehow from this formal procedure out pops something that is not the derived category of K, but it's some closely related gadget that's remembering sort of all of the tangent information at K, and the tensor product on it is actually like a natural thing coming from Tor. And so maybe let me not write down the others, but you could ask what happens in the other examples. So I could do this from around a K theory, choosing a P and an N. And if you guessed that I would get graded comodules over the Hopf algebra of stable co-operations, you would be right, because that is what I would get. And then life is, again, harder in the case of stable categories. But maybe let me write down one example. So I could take a cyclic group of order 2 are copies, so elementary abelian 2 group, and I could pick a cyclic shifted subgroup. So I'm talking about what happens at some closed point on the spectrum, and then the category I would get would be comodules not graded for the exterior Hopf algebra on a vector space of dimension r-1. So this r-1 is corresponding to the rank. It's like you've got some projective space around, and I take comodules over this with the usual Hopf algebra structure, but there's no grading.
Are you talking about the minimal prime? Are you talking about the minimal prime?
No, I'm talking about any closed point, right?
Closed point.
Yeah, so I'm picking, so we can take K algebraically closed, and so I pick a closed point, so it corresponds to this cyclic shifted subgroup given by the projective coordinates, and this will be the residue field at that point. And I mean, if this looks a bit funny, in particular the lack of grading, you might be convinced by the fact that, like by causal duality, this is not so far away from projective space. I've just collapsed some suspensions, and this looks a lot like tangent information at a closed point on the corresponding projective space if I had the grading.
Yeah.
Right, and that is a good time to stop since I've gone over time, so I will stop. Thank you.
Thank you.